Swayam Prabha. Digital India. Educated India.
In the last lecture, we have discussed about the transfer functions for the short period dynamics in the longitudinal motion. In today's lecture, we'll be discussing the Fugit dynamics and how we can find the transfer function for the Fugit dynamics. First, let us rewrite the natural dynamics or the Fugit approximation. The Fugit approximations had, if you remember, we had delta u dot delta theta dot equal to xu minus g minus zu divided by u naught 0 and the state vector delta u and delta theta. This is the equation we had for the Fugit motion. Let us refer another equation for the delta w dot from the linearized equation of motion of the longitudinal dynamics. Delta w dot can be expressed as, if you refer the equation, we can write, so the longitudinal motion, the linearized longitudinal motion, we had 4 degrees of freedom equation, or we can say in terms of state variable, we had delta u dot, delta w dot, delta q dot, and delta theta dot. So this is the variable in the longitudinal motion. So if you take this equation delta w dot, we have zu delta u plus zw delta w. Please refer the equation, longitudinal equation. You can get this delta w dot equation. U naught delta q minus z sine theta naught delta theta plus g delta u capital delta u plus g delta t capital delta t. Now, for the Fugit approximation, what you have assumed, again, for the Fugit approximation, if you remember, we had delta alpha equal to delta w divided by u naught, and in this case, we can assume if u naught is very high value, then delta alpha we can assume to 0. And in this condition also, we can write delta w equal to 0. Again, we can write delta w dot equal to 0. Now, based on this assumption, we have another assumption also. If you consider the reference angle for theta, which is theta naught, equal to 0. So this is, we can assume the trim condition, trim value of theta. So if you assume these assumptions in this equation number 1, this is equation 2, and if you substitute this assumption in equation 2, we can write 0 equal to zu delta u plus u naught delta q plus g delta E, capital delta E, plus G delta T, capital delta T. Further, we can write U naught delta Q equal to minus GU delta U minus G delta E, capital delta E, minus T. And from this delta Q, you can write delta theta dot minus ZU U naught delta U minus G delta E U naught capital delta E minus G delta T U naught T. If you consider the control in equation 1, if you apply the control, so here we can write the equation 1 with the control input. We can write delta U dot delta theta dot equal to, we can the same state matrix, which is XU minus G minus ZU divided by U naught 0, and the state vector delta U delta theta, and the control matrix we can write from the longitudinal motion equation. If you refer, it will come X delta E, X delta T, and for delta theta we can write minus, for delta theta dot, the control input, minus G delta E U naught and minus G delta T divided by U naught. And the control input, this is a control vector, and the control input will be delta delta E delta delta T. This is the control input. Now, from the state space form, this is equation, let's define this, the equation number 3. From equation 3, delta U dot can be written as, we can write delta U dot equal to XU delta U minus G delta theta plus X delta E, capital delta E, and plus X delta T and capital delta T. If you apply the Laplace transform, applying, let's find this equation number 4, applying with 0 initial conditions, because the transfer function we are going to find and it is valid with the 0 initial conditions. Applying Laplace transform with 0 initial condition, equation 4 yields, and write X delta US equal to XU delta US minus C delta theta S and plus X delta E capital delta ES plus X delta T capital delta T S. And here, so one more thing, the reason we found this expression, if you are having this expression also, we can find the delta Q also. And here actually we are writing delta theta dot term, and this is nothing but delta Q. So this is the main motivation. And now from this equation, we can further write S minus XU delta US plus Z delta theta S equal to X delta E, capital delta ES plus X delta T delta TS. Here, if you notice, there are two control input are one is capital delta S and capital delta TS. But as per the analogy of the transfer function, we can find only possible if you are having the CISO system. But here we are having two inputs. So we have to assume one input at a time. So here what you will do is set delta TS equal to 0 and divide by delta del ES on both sides of the above equation. We can write S minus XU delta US delta ES plus G delta theta of S delta del ES equal to X delta E. Let's define this equation number 5. Now we'll work on the second equation, second ODE equation. From equation 3, we can write delta theta dot from equation 3. Delta theta dot can be written as delta theta dot equal to minus GU U naught delta U minus G delta E U naught delta E and minus G delta T divided by U naught capital delta T. Now applying Laplace transform to the above equation with 0 initial conditions yields we can write S delta theta S and we can write equal to minus GU U naught delta US minus G delta E U naught delta del ES minus G delta T U naught delta del TS. And from this we can further write Z U naught delta US plus S delta theta S equal to G delta E U naught delta ES minus G delta T U naught delta del S. So now here if you notice again here we are having two control input. So here again we'll consider delta T capital delta TS to be 0 and we'll consider only the elevated angle to the system. So here set on delta del TS equal to 0 and divide by delta del ES on both sides. Here it's, we can write ZU U naught delta US divided by delta del ES plus S delta theta S divided by delta D del ES minus Z delta E divided by U naught. So here we are actually looking how the delta US and delta theta is going to be effective with the application of control input delta del ES. So we are not considering the thrust vectoring here, thrust control or propulsive force to the system. Only you are considering the how the elevator going to be affected for these states delta US and delta theta is. If you remember in the last lecture, we have done another method, which is basically we have used CSI minus A inverse B. So if you are going to use this method to find the transfer function, so here we have to modify C matrix and B matrix. So if you are going to find delta US with respect to delta del TS, and if you are going to find delta theta S with respect to delta del TS, then we have to modify the B matrix. So in the present case, what you are doing now here, so here we are considering the B matrix. If you look at the state space form here, here in the state space form, in the control matrix, we are considering the first part, the first column of the control matrix. And if you are going to find how delta U and delta theta are going to be affected with the delta TS, delta del TS, then we have to consider the second column of the control matrix. So here for the time being, we are considering only the first column vector of the control matrix. So you can use this method also, and you can find the transfer function of the respective output. So now let's go back to our problem. So here we can form the matrix in the matrix form. So let me define this equation number. This is the equation 5, and this is, so using equation 5 and 6, using equation 5 and equation 6, we can form the matrix, you can write the equation in matrix form. So here we'll have x minus xu z2 divided by u naught s, and the transfer function delta us. So here only you are looking how the delta del es going to affect to the system, I mean the output delta us, and delta theta is with respect to delta del es. And the B matrix, so as I said, we are only considering the first column matrix, first column matrix in the B control matrix. So here we are having the x delta E and minus z delta E and U naught. This is exactly what you are getting. You see, this is the last element of this vector, and this is also the first element of the vector. So only we are getting the first column vector of the control matrix. Now let's assume this is our A, this is X, and this is B, for example. So here this is indicates X1 and this indicates X2. So which is basically X1, X vector. Yeah. So now we have to find X1 and X2, which are basically transfer function. Let's find first so you'll apply here the Cramer's rule, the brute force method. So for that, we have to find the determinant of the A. So let's find the determinant of A comes out to be s squared minus xu s minus j2 divided by u naught. Using camera rule, so this part will be remain to be same as a denominator for both the transfer function. So using Cramer's rule, we can find A1, B. This matrix can be formed as x delta I G minus G delta I divided by U naught S. And the determinant of this comes out to be x delta I S plus G Z delta I divided by U naught. So we can find the transfer function x1, which is basically delta US divided by delta del ES, which is basically this is basically the numerator part. So x delta ES plus G Z delta I divided by, so this is U naught, and the determinant of A matrix, this is square minus xu s minus g zu divided by u naught. This is basically we are applying this a1 b divided by a. This is what you are getting. Now we'll find the second transfer function, which is basically delta theta is divided by delta del es. So in this case, again we have to find again a2 b vector, which is we can form the matrix S minus xu x delta I 0 divided by u naught z delta I divided by u naught. And the determinant of this comes out to be minus z delta I divided by u naught s plus xu z delta I u naught minus x delta I z2 u naught. And the transfer function we can find, so x2 you can find delta theta is divided by delta del es, which is a2 b divided by a determinant, which comes out, this is the numerator part, so minus g delta I u naught s plus xu g delta I u naught minus x delta I cu u naught, and divide by the determinant of A, so which is s square minus xu s minus g z2 divided by u naught. So we have found the transfer function, or this is how the delta theta going to be affected with the control input delta es, and here how the delta us going to be affected with the control input delta es. This is very important because, as I said, that finding transfer function, of course, very important thing. So once we have the transfer function, we can apply the conventional method of or classical control method for designing the control algorithm. And these are the few examples we have discussed so far. The same way also we can do the for the rest of the state space representation what we have derived before for the lateral directional motion or any other state space form we have found so far. So we can apply this concept to come up with the transfer function, and if you are having transfer function, we can design the control algorithm. So this is basically the GPS. Here actually this is the GPS. So we have to design GC of S, and this is the summing point where we are having, for example, if we are going to design the control algorithm for this system, so we can set theta desired is, and this is plus, this is minus, negative feedback. So here we are having delta theta is, This is the controller which is giving the control input to the system, and we can, if the control is stable, delta theta s, we can track to the digital value of theta. So this is how we can design the closed loop control system, what we have discussed in the first half of in this course. There are a lot of techniques we have considered how can come up with the PID, PD controls using defined concept. So in the next two lectures, we'll be discussing how we can come up with the controls as well as transfer functions together. Thank you.